Hi, my name is Christopher Crognale.
My name is Ariel Wise, and we are both mechanical engineering majors with an aerospace concentration at the Catholic University of America. Today, we'll be discussing our presentation on the modeling of sound attenuation in tall grass, a sustainable noise control strategy for airports and spaceports. The motivation for research is to find a sustainable solution to support the increase in the commercialization of supersonic and hypersonic flight. As it is already, airports and spaceports are quite noisy and cause health concerns to the humans and disrupt wildlife. The approach we are taking to solve this problem is using tall vegetation, such as grass, as a substitute for acoustic barriers as they are not sustainable over time. As you see in the pictures on the bottom left-hand side, there's a current acoustic barrier, and then our approach suggestion with adding tall vegetation to it. We are modeling this in a laboratory setting through 3D printed samples that could fit into an impedance tube where we can test it with sound and get the acoustic properties of samples over time and use a numerical solver to predict sound effect. Spaceports are usually placed in very remote places, either coastal or desert, as you can see the Mojave for the desert and Vandenberg and Wallace for flight. These ultimately have no effect on humans and wildlife as there's not much around it. Compared to airports, which are placed away from cities, but ultimately cities go around them. And a prime example of this could be Austin or Baltimore, Washington. But for this presentation, we are specifically focusing on Dulles as it's most relevant to us, and as well as it has a great ratio of vegetation to structures as seen on the left-hand side. Continuing with Dulles, we can look into a noise map that shows us that on the east side runway of Dulles, there is a lot of takeoff and landing, suggesting that there's a high noise level, which is presented by the red for the DNL, which is the day-night average sound level. And lastly for the method, we're using blades that replicate 3D grass samples through an impedance tube that are modeled with two different orientations at 0 degrees and 45 degrees, that as the sound goes through, we can see how sound travels and affects and ultimately figure out the propagation of sound through grass.
The way we test these samples is through a device called an impedance tube that measures the characteristic impedance, Z, and wave number, K, of a given material by running two experiments with two different air gaps. In this case, we are measuring the grass models at 0 degree and 45 degree orientations. The aim of these experiments is to determine the attenuation coefficient, which effectively tells us how the sound pressure, or noise, is reduced per unit length, which in this case is meters. This plot shows the relationship between the attenuation coefficient and frequency. It's important to note that the orientation doesn't have an effect at low frequencies, which are the frequencies we're concerned with, as low frequency sound waves propagate over longer distances, which thus is an important facet of this study, since the noise generated by an airport runway that is intrusive travels at low frequency. So the idea is to replace the tall vegetation with an equivalent fluid with a complex wave number, which effectively tells us the acoustic attenuation of the vegetation. Using the parabolic equation solver developed by our group, we can modify the solver to replace a certain volume of the surrounding fluid, air, with the vegetation, and thus predict sound pressure levels inside and in proximity to the vegetation more accurately. In this image, we also include the effects of the boundary condition that soil presents, Z ground. Simulations were run, and these plots resulted, displaying the excess attenuation over the spatial field. This excess attenuation includes the attenuation introduced by anything other than the spreading law, which says that sound waves will decrease in energy over space, or absorption, and this includes refraction, ground absorption, and surface roughness. The first plot shows the surface impedance for the short grass based on the boundary conditions. The second plot shows the tall grass study represented with the complex K, and the third plot is the difference between the first and second plots. And for all these plots, the source is on the left and at 2 meters high. The bottom plot, showing the distance between the top two, is divided into two sections. The first 50 meters contains a hard surface, such as asphalt, while the final 50 meters contains the grassland. The bottom plot can either represent a surface impedance or an equivalent fluid. When we compare these plots, it can be seen that a reduction of 6 decibels occurs from the presence of the tall grass, effectively reducing the sound pressure by a factor of 2. But through our research, we've been able to design and 3D print synthetic grass blades to predict the acoustic effects of real grass surrounding air and spaceports. By testing with an impedance tube, the complex wave number of the blades have been determined, and this, plugged into our numeric solver, predicts the excess attenuation introduced by the grass. These predictions show that the tall grass can reduce bothersome noise around these ports by a factor of 2, 100 meters from the source. We thank you so much for your support and on our research. Thank you.